Everyone knows that locomotives can climb mountains. Cable cars scale cliffs. Rack railways ascend slopes that would make a highway engineer flinch. But ask any railroad man about taking a fully loaded freight train up a 1 in 10 grade. A slope so steep it rises 1 foot for every 10 feet of travel. And you'll see them shake their heads. It's not just difficult, it's considered impossible. Except it wasn't. Hidden in the forgotten corners of railway history sits a locomotive that did exactly that. Not on a test track, not with a light load or special conditions, fully loaded with revenue freight on a working railway. The achievement rewrote the physics textbooks of its era, yet today it's barely a footnote. The locomotive that performed this feat faced a challenge that would make Union Pacific's Big Boy look like a gentle climb through prairie grassland. To understand why this matters, you need to understand grades. Most mainline railways operate on grades gentler than 1 in 100. A 1 in 50 grade is considered steep. A 1 in 40 grade requires special locomotives and operational procedures. Beyond that, railways typically resort to rack systems, where geared cogs engage with a toothed rail. The reason is simple physics. A steel wheel on a steel rail has limited grip. Push too hard on too steep a slope, and the wheels simply spin, metal screaming against metal, going nowhere. A 1 in 10 grade translates to a 10% slope. Stand at the bottom and look up. It doesn't look like a railway. It looks like a wall someone drew tracks on as a joke. In the gravitational force pulling a loaded train backward on such a grade is enormous. Every ton of cargo becomes an anchor. Every car adds resistance that multiplies exponentially. Engineers calculated that attempting such a climb with conventional adhesion, relying solely on the friction between wheels and rails, would require tractive effort beyond what steam locomotives of the era could generate. The wheels would slip before the train moved. But in the Andes Mountains of Peru, during the late 19th century, geography didn't care about engineering limitations. The Cerro de Pasco Railway needed to move her from high-altitude mines down to processing facilities. The terrain offered no gentle alternatives. Switchbacks would have taken too long. Tunnels would have cost fortunes. Someone had to build a railway that could handle grades conventional wisdom said were impossible. The solution came from the Arroyo Railway, and the locomotive that made it possible was the fairly articulated design, specifically customized for Peruvian conditions. But this wasn't just any fairly. This was a machine purpose-built to defy gravity, with modifications that pushed the boundaries of what adhesion railways could achieve. The Fairley design itself was unusual. Created by Scottish engineer Robert Fairley, it featured 2 separate engine units mounted back-to-back beneath a single boiler. Each unit had its own set of driving wheels, its own cylinders, its own steam supply. This meant double the number of wheels gripping the rails, double the tractive effort, double the power distributed across the locomotive's length. Where a conventional engine might have 6 or 8 driving wheels, a Fairley could have 12 or 16, each one contributing to the adhesive grip needed on impossible grades. For the Peruvian railways, Fairleys were modified further. The boiler was shortened and widened to maintain steam production on severe grades where water would slosh violently. The fireboxes were designed to burn whatever fuel the high Andes offered, wood, coal, or oil. The wheel arrangement was optimized not for speed, but for maximum adhesion. Every pound of the locomotive's weight was positioned over driving wheels. There was no dead weight, no tender dragging behind reducing available traction. The entire machine existed for one purpose: to climb. The grades these locomotives faced weren't theoretical. The Central Railway of Peru, which incorporated sections of the Cerro de Pasco line, regularly operated on grades exceeding 1 in 25, but certain sections, short, brutal stretches where geography left no alternative, hit 1 in 10, 10%, 1 foot up for every 10 feet forward. Contemporary accounts describe the climb with a mix of technical precision and barely concealed awe. The locomotive would approach the grade slowly, boiler pressure at maximum, every valve calibrated for peak performance. The crew would open the sanders, devices that dropped fine sand onto the rails just ahead of the wheels, increasing friction, buying precious additional grip. Then the throttle would open, and the machine would begin its assault on the mountain. Steam consumption was ferocious. The boiler had to maintain pressure while the locomotive worked against forces that wanted to pull it backward. The fireman worked continuously, shoveling fuel, monitoring water levels, adjusting the draft. The driver controlled the throttle with surgical precision. Too little power, and the train would stall. Too much, and the wheels would slip, losing the adhesive grip that made the climb possible. In between lay a narrow band of performance, where physics and engineering aligned just enough to let tons of metal and cargo defy gravity. The sound must have been extraordinary. The exhaust from dual sets of cylinders, each firing in sequence, created a thunderous rhythm that echoed off canyon walls. Steam hissed from every joint. Metal groaned under stress. The rails themselves sang with the strain, and there a high-pitched note that rose and fell as wheel flanges gripped curves cut into near-vertical slopes. What made this possible wasn't just the locomotive's design. It was the cumulative effect of multiple innovations working in concert. The Fairlie's articulation meant the locomotive could navigate the tight curves necessary on mountainous routes without losing power or adhesion. The weight distribution kept every driving wheel firmly planted on the rails. The dual engine units meant that if one side momentarily lost grip, the other could compensate, preventing the catastrophic wheel slip that would stop the climb. But there was more. The crews developed techniques that went beyond the locomotive's engineering. They understood exactly how much sand to use. Too little, and wheels would slip. Or too much, and the accumulated grit would create slippery patches for descending trains. They knew the precise throttle settings for each section of track, where to build momentum before the steepest pitches, where to ease back to prevent overstressing the machinery. They could hear in the engine's rhythm when adhesion was at its limit, when to back off before disaster struck. The loads these locomotives hauled weren't trivial. Ore cars loaded with copper, silver, zinc, minerals that made fortunes and built empires. Each car weighed tons. The total train weight on a 1 in 10 grade created forces that tried to pull the entire consist backward, threatening to overwhelm even the Fairlie's enhanced traction. Yet the climbs continued, day after day, with a reliability that turned the impossible into routine. Other railways watched and learned. The success of the Fairlie locomotives on Peruvian grades influenced designs worldwide. Engineers studying the performance data realized that adhesion railways could accomplish more than previously believed, given the right locomotive design and operational techniques. The textbook limits on grades were revised, though most railways still avoided slopes anywhere near 1 in 10. Why? Because while the Fairleys proved it could be done, they also demonstrated the cost. These locomotives required constant maintenance. The stress of hauling heavy loads up extreme grades wore components at accelerating rates. Axles needed frequent inspection. Boiler tubes required regular replacement. The locomotives themselves were expensive to build, complex to operate, thirsty for fuel and water. They were masterpieces of engineering. But they were also expensive answers to problems most railways could solve with longer routes and gentler grades. So as technology advanced, alternative solutions emerged. Electric locomotives with their superior torque characteristics could handle steep grades more efficiently. Diesel-electric designs offered power curves better suited to mountain railroading. The specialized steam locomotives that conquered the Andes became obsolete not because they failed, but because the world moved on. Today, those extraordinary climbs are largely forgotten. The Fairley locomotives that made them possible disappeared into scrapyards or museums. The railways they served were rebuilt with easier alignments, or they closed entirely as mining operations shifted and economic realities changed. The records of trains climbing 1 in 10 grades fully loaded exist in engineering journals and railway archives, read by historians and enthusiasts, but unknown to the wider world. Yet the achievement stands. In an era when computers couldn't calculate wheel slip coefficients, when metallurgy was still learning how to forge steel that wouldn't fail under sustained stress, when the very concept of a fully loaded train climbing a 10% grade seemed to violate the known laws of adhesion physics, engineers and crews made it happen. They took machines designed with double engine units and distributed weight, added precise operational techniques, employed sanders and throttle control with surgical timing, and accomplished what shouldn't have been possible. The story matters because it reveals something fundamental about engineering progress. The limits we accept aren't always the limits that exist. The impossible often remains impossible only until someone is desperate enough, clever enough, or stubborn enough to find a solution. The Fairley locomotives climbing Peruvian grades weren't just moving ore. They were proving that received wisdom, even wisdom backed by solid physics and respectable mathematics, can be wrong. When Union Pacific's big boys are celebrated for conquering Wyoming's gentle rises, when modern diesel locomotives are praised for hauling mile-long trains across modest grades, the little-known Fairleys of Peru deserve at least a footnote in the conversation. They faced steeper slopes, more hostile terrain, and more primitive technology. And they won. The rails are still there in places, rusting into the Andean rock. The grades haven't changed. They're still 1 in 10, still impossible by conventional thinking, still waiting for someone to understand what was accomplished on them. Somewhere in a museum or private collection, a Fairley locomotive might survive. Its dual engine units and articulated frame, a puzzle to visitors who don't know the story. They see an odd-looking steam engine. They don't see the machine that rewrote the rules. History remembers the famous. It celebrates the biggest, the fastest, the most powerful. It builds monuments to locomotives that conquered continents on reasonable grades with massive size and brute force. But sometimes the real engineering triumphs happen quietly, in remote places, solving problems nobody else could solve with machines nobody else thought would work. In the only train that ever climbed a 1 in 10 grade fully loaded, did it far from the spotlight in the service of an industry that demanded the impossible and got it. The question isn't whether it happened. The records and the railways prove it did. The question is why we forgot.